Okay, so we're very happy to welcome Grisha, who will talk about DMRG for spin systems and lattice gauge theory.
All right, thank you so much. Yeah, it's going to be maybe very practically oriented 2 lectures, and maybe the most practically oriented. So it will be a little bit of theory, but then at the end, I'm going to show Mathematica files, which everyone can download from GitHub folder. So it's github.com/GRP/EITB 2002. So the short plan. So I'm going to start today with maybe the simplest model, the simplest spin chain, which is called so lecture 1, XY spin chain, homogeneous spin chain. So I'm going to show how to solve it exactly theoretically. Exact solution. Then I'll briefly discuss how to use what we call exact diagonalization. For this model. And finally, I'm going to discuss the method which is called density matrix renormalization group. Group DMRG, which goes under more general name tensor networks, which in the tensor networks, it's a set of different methods to try to solve 1+1 dimensional quantum systems or 2+1 dimensional quantum systems. So in 1+1 dimensions, these methods work amazingly well, and the real challenge is to push them to higher dimensions. But in these lectures, I will focus only on 1+1 dimensions. And at the end, I will demonstrate this Mathematica files, which everyone can download from here, just to show that it's very easy to program this and get some results, or test your exact solutions. So if you can solve these models exactly, you can always try to test them numerically. And just going ahead, lecture 2 will be about the same numerical methods, but for Schwinger model. Schwinger model in 1+1 dimension, and I'm gonna show how to use Hamiltonian approach. Hamiltonian approach to this Schwinger model. How to put it on a lattice using the construction by Kogut and Susskind, which is called staggered fermions. I'll show that at the end, this model basically described by 1+1 spin chain with sort of non-local interaction, and then the same method can be applied to this model. All right, so it's a short plan. Okay, let's start with XY model. So the Hamiltonian for the XY model, it's a spin system. It's let's put some coupling J, sum over 1 to n-1 plus I x I plus 1 x I y minus I plus 1y, where where Si, the spin 1/2 operator is Six y, z is just a vector of 1/2 of Pauli matrices. All right, so for simplicity, let's just set this coupling. Nothing depends on this coupling in our case, so it just lets it set to 2. And we're gonna solve this model theoretically. For this, let's introduce sigma plus, sigma minus operators, which are plus minus I, which are 1/2 sigma x plus minus I sigma y. And in this case, this Hamiltonian can be written in a simple form, which is just sum over I sigma I plus sigma I plus 1 minus sigma I minus. Right. So the sigma plus sigma minus, just matrices, 2 by 2 matrices. Check this simple form. And to solve this, so this model was first solved by in the old paper by Lieb, Schulz, Matisse in 61. And to solve this, we go to we do what we called Jordan Wigner transformation. Namely, we pass from spin variables to fermionic variables. And so let me write this. So I can define my fermionic variable Ci as a product of sigma z matrices. J goes from 1 to I minus 1 times sigma I plus. And Ci star dagger is same sigma I minus. So one can check that these type operators, Ci and Ci dagger, they now anti-commute. So their anti-commutator is the delta Kronecker, and also sigma z operator is 2 Ci minus 1. All right. So to be more, precise, when we write these models in this form or this Jordan Wigner transformation, what we really mean is the tensor product of this matrices. So this operator Ci is actually a tensor product of I operators like this. That's what I denote by I don't usually use this notation of tensor product just to save some space, but that's what we really mean for these operators, and the same for the Hamiltonian. When we write the Hamiltonian in this form, we usually keep in mind the tensor product of operators on different spin sides, chain sides, times this identity matrices which live on the chain side. So each identity matrix is just 1, 1. So the Hilbert space of our system is, so we have n sides. So the Hilbert space, dimension of the Hilbert space is 2 to the n. And each of this operator, it's actually a matrix of 2 to the n times 2 to the n. Right. So yeah, please ask me any questions if you have. The goal is to be the most explicit as possible here. All right. So now we use this Jordan-Wigner transformation. We put this we put this transformation into this Hamiltonian, so we can rewrite the XY Hamiltonian through the fermionic operators, and the answer will be so it's quadratic in this fermionic operators, and I can write them as a Tij, Ci star J, J. Yeah, so I can introduce this matrix Tij, where Tij is an n by n matrix, which has 0 on diagonals and 1, 1 off diagonal, and 0 everywhere here. So now to solve this system, I need to diagonalize this matrix Tij, which can be done exactly. Right. So finalized solution, I just need to diagonalize this matrix Tij, and spectrum of this matrix, I call it epsilon k. So it's a single particle energies. I can write it as a -2 cosine phi k over n plus 1, where k goes from 1 to n. And so if you can, so now with this spectrum, I can write my Hamiltonian, XY Hamiltonian, is just sum over epsilon k, some new operators, new fermionic operators, C twiddle k, C k. K goes from 1 to n. Yeah, so it's completely diagonal now. So this new operator Ck will also satisfy fermionic relations. And so now to find many bodies, so this is called single particle energies. And to find energy levels of the Hamiltonian, we basically need to fill our states by these fermions. So the spectrum epsilon k looks from -2 to +2. So it's a cosine. So it goes like this. 1, 2, ... We have n spots of energies, and filling them in different way will give us many body energies of the XY Hamiltonian. So the ground energy for the XY Hamiltonian corresponds to filling all the lowest energy states here. So I have to fill out all these states which are below, which have negative energy. So then the answer for the ground energy will be sum over this epsilon k from 1 to say floor of n over 2. So that would be the ground energy. Right. And the excited states, they obtained by just filling the spectrum in a different way. So I can move, say, just can remove one state here, and that's will increase my energy, or so I can just play with this, combinatorially play with this Hamiltonian, and the ground state corresponds to the filling all the slowest energy states. So I can write it as a 1 in a second quantization notation. It's 1, 1, 1, 1, 1, 1, and then 0, 0, 0, 0. So I filled all states until n over 2, and all states which are greater than n over 2, they're unfilled. So that's the ground state. Yes, sure.
This CK
Mhm. Yes, exactly.
Why is it that ground state has half of the states? And why is not just one particle in the lowest?
Oh, because you want to find the state with the minimum energy. So you want to find configuration of particles such you can get the minimum possible total energy. And if you can add some negative energy to you will make it smaller, right? So for example, if the state which is all zeros will have energy 0, but that won't be the ground state. It would be some.
So the first state would be just removing one.
Removing, yeah, exactly. All right, so that's a theoretical solution, but the idea is that we can solve this model numerically, and the first kind of trivial way to solve this, okay, I have to speed up, is to just which is called exact diagonalization, is just to build this model on a computer, is just to build this Hamiltonian in terms of spins as a big matrix. So it's a 2 by 2n cross times 2n matrix. So exact diagonalization approach would be to just build HXY on a computer as a 2 to the power n times 2 to the power n matrix, and just diagonalize this matrix and find its energy levels, and they have to coincide with what we found theoretically here. Yes. All right, so yeah, thank you for this question. So here I use open boundary conditions. So there's no, so it's just a chain. So I don't have any term which connects side 1 with side n. So it's open boundary conditions. So this matrix, in this case, if I would have periodic boundary condition, I would have 1 at this point here. So I have 0. So it's open. It's a chain with open boundary conditions. So open boundary condition. Yeah. No. If you have periodic boundary condition, that will slightly change here. There will be some. I think there will be maybe n here instead of n plus 1, something like that. Yeah, this is for open boundary conditions. All right, so.
I was wondering, can you use some AC answers to solve this problem?
I think this can be solved even without the Bayesian ansatz because it's the simplest type of model. But there are models like Heisenberg models or more complicated models which have Bayesian ansatz solution for some, so for ground energy or some. Yeah. I chose this model because it's the simplest one, and we can solve. Basically, we can understand it theoretically exactly in some way.
And the fact that you have this ground state and not a symmetric combination of pins at all the sides is a consequence of the fact that you are not imposing periodic boundary conditions. This is in.
Yes. That's a good question. Maybe not. It's so simple that probably it can be solved in some other way, but it's kind of the standard technique, which was, I think, used in the first paper. Yeah, I don't know. I think it's the idea is to bring it to quadratic form, to diagonal form. Looks like that's the way. All right, so exact diagonalization is basically just building this matrix on a computer and diagonalizing it and finding its eigenenergy levels. So I'm going to show it quickly at the end of this talk. But let's go to the method, which is one of the methods of tensor networks, which is called density matrix renormalization group. So the problem with exact diagonalization is that if we increase the number of sites, so if number of sites become big enough, the matrix the size of our matrix exponentially grows with the number of sites, and at some point it becomes numerically intractable because you can diagonalize very huge matrices on the computer, on a classical computer. And I think the state of the art for exact diagonalization is when the number of sites is maybe like 34 or 36. So this would be the limit which one can do using exact diagonalization. Nevertheless, remarkably, using this tensor network methods or this density matrix renormalization group method, you can find energy levels, lowest energy levels or expectation values of different operators and other properties for this type of 1+1 dimensional chains for almost arbitrary n. So you can go to n equals 1000. Yes.
Yes. You mentioned we cannot diagonalize in classical computer.
In principle, yeah, that can be done in quantum computer, but
Quantum computer every
if say it again.
From the computational complexity side,
Mm-hmm.
quantum computer it has some advantage.
I don't know much exactly how one can approach this problem using quantum computer, but yeah, I don't know. But that's what we usually believe, that somehow quantum computers can solve large quantum systems, I guess. But for this, we don't need quantum computer. That's the point. We can solve this using, at least for lowest energy states, we can solve it using density matrix renormalization group, which I'm going to discuss now at the end of this talk. So the idea is basically to start doing renormalization group, meaning that we at some point we should throw away some irrelevant, I would say irrelevant part of the Hilbert space or irrelevant degrees of freedom, and project on the degrees of freedom of the Hilbert space, which are important for the ground state or low excited state. And for this, what we do, we first need to understand how to build this Hamiltonian side by side. And in this simplest model, one can show that if I have say XY Hamiltonian, which is defined on k sides, 1, 2, 3, dot k. So if I have h k, so then I can build h k k plus 1, adding one side, using a simple rule, which is h k plus 1 is Hamiltonian hk, tensor product of identity matrix of this k plus 1 side. Let me call it I1, meaning that it's just the identity matrix of one qubit on one side. So it's 2 by 2 identity matrix, plus the term which connects k and k plus 1 sides. And I can write this term as identity matrix of all k minus 1 sides, k minus 1 qubits, tensor product of sigma plus k, sigma minus k plus 1, plus sigma minus k, sigma plus k plus 1. So there's a simple rule to build XY chain, or any other for any other models. You can also derive this type of rule where if you have Hamiltonian for k sides, you can build Hamiltonian for k plus 1. And all right. All right, so we can build the spin chain side by side. And what we can do in density matrix renormalization group, we basically partition our system on the left and right sides. And we call the left side, the left spin chain as a system, or left. And we call the right spin chain, which as the environment. And this Hamiltonian is what is called left block or system block. This Hamiltonian, which represents this spin chain, is called right block. And from this left and right block, we can construct a chain of 2 k sides. So each of this chain is k sides. And the bigger block is called the superblock. Which will be h left k, it's called k, meaning that it's made of k sides times identity plus identity times h right. And there's a term which connects this left and right blocks, and it's made out of sigma plus sigma minus spins. So it's sigma plus left k times sigma minus right k, sigma minus left k. Okay, where right, so where sigma plus, can you see here? So sigma plus left k is identity k minus 1 times sigma plus, and sigma plus right k is sigma plus. Like this. All right, so far we just, what we're doing here, we're just building this chain using kind of its block structure. So we don't do anything fancy. So we can build left block, we can build right block just using the Tensor product. And then we can, out of left and right blocks, we can build the super block using the simple formula according to our XY model. And but now the most important part starts is that, okay, so we can diagonalize the super block. So we can find the, let's say we're interested in the ground energy. Was we interested in this ground energy? So we can diagonalize the super block, and it gives us the ground energy for 2k spin chain. So I have to solve this Schrodinger equation for 2k spin chain. All right. So I'm looking for the ground state of this chain, and at this moment everything is exact. So I didn't do any renormalization, any truncation. So I'm just essentially doing part of what I would call exact diagonalization, right? So just diagonalize this matrix, and I find energy, state, and wave function. So now, okay, so now the most important part about this density matrix renormalization group is to start doing renormalization or truncation of our degrees of freedom. And for this, let us write the wave function, the ground wave function, ground state, as a tensor product of left and right left and right blocks. So it will be sum over I and j from 1 to 2 to the k, where 2 to the k is the Hilbert space dimension of left block and right blocks. There will be coefficients ij, and here I left as a product of j right. So I can always write my ground state of this superblock as a tensor product of states of left and right blocks connected by multiplied by coefficients psi j. Right. And in this point, I can define what we call density matrix, and I can define density matrix for the left left side block and for the right hand side block. So for the left hand side block, let me call it rho L, will be trace over the environment, or trace over the right hand side states of my ground energy state psi. So meaning that it's going to be sum over j from 1 to k trace jr psi j. So this is my left density matrix, and if I compute this trace, I can write this density matrix through this psi. So it's going to be psi ij psi star I prime j sum over j. Okay, so rho L I prime. So it's just the product of, or in a short notation, rho L is psi dagger, where psi is this state, is my state. So I can think about the state as a matrix, and I can build the density matrix of the left system as a psi dagger. Similarly, I can build the density matrix of my right block, tracing out the system or left block. So this, and in matrix notation, this will be psi dagger psi transpose. Okay. All right. So this is density. Density matrices. All right, so density matrix is a Hermitian matrix, and moreover, it's a positive matrix. So if I diagonalize density matrix, its eigenvalues, let me call them pi, they are probabilities. So they are less than 1, bigger than greater than 0, and they have to add up to 1. So if I sum over all eigenvalues of my density matrix, to the k, I'm gonna get 1. Right. So let me order them from bigger number to lower number. So P1 is bigger than P2, P2 is bigger than P3, and so on. So let me order them. And we have to P to K. So usually what happens in the gap system, so if we plot this eigenvalues of the density matrix, P is 1, 2, dot, dot, we'll see that they decay almost exponentially fast. So there will be a few eigenvalues which is very close to 1, and then all other eigenvalues are going to be very, very small. And that's usually, yes. So now we do the most important part of this procedure. We do truncation, or in other words to say renormalization. So what we do, we throw away lowest probability states. So we throw away states of our system, which have lowest probability, which have lowest eigenvalues of the density matrix. So we keep only, so initially, since we had k side chain, we have 2 to the k states, but now we keep only m states, m biggest probable states. Keep m states where m usually is of order hundreds or tens, and it's much smaller than 2 to the k. And we can see that the error, well, truncating at least the state, we can estimate error. This is called truncation error. Truncation error would be just essentially 1 minus sum of probabilities we keep. So from I to m. So if we, or probabilities we throw away. So truncation error is the sum of all probabilities we throw away, or 1 minus probabilities we keep. And usually in this type of computations, if we keep, say, only like 10 or 100 states, this truncation error is extremely small. It's because, as I said, they fall off exponentially. This truncation error may be like 10 to the minus 10, or it's extremely small number. Yes, yes. A good question. I don't know, yeah, how to estimate. Mm-hmm. Can you give some examples? Good. Yeah, so the reason for this is basically entanglement between left and right blocks, and if it's this entanglement, so the number of states we usually have to keep is proportional to e to the entanglement entropy between left and right blocks. So if your system is highly entangled, then it's not going to work. So if your left block is very entangled with the right block, then you have to keep a very large number of states, and the whole method may not really work. Yes. Yeah, that's true. So the regional, the method applies only for a few lowest excited states, and if you want to apply it to some, I don't know if you can apply it successfully to some higher excited states. And, yeah, so. Yeah. Yeah. I mean, there are always like clever tricks to rewrite the system you're looking at some different kind of, not maybe in real space, but maybe in momentum space, or do some kind of tricks, and then this method maybe magically applies. So it's kind of art to adopt this, to do a renormalization group in some way, sort of to throw out some irrelevant degrees of freedom. Yeah, that's. All right, so let me just finish the idea of this. So we keep this, so this is the main idea. So we keep this, and actually, yeah, sorry, I had to say that this method was first proposed by Stephen White in 92. And basically it's coming from condensed matter community. and it successfully was applied to many condensed matter models, and already applied to some QED Schwinger model. So to finish this idea, so we keep only highest probability states of our density matrix, and let me build a matrix. So if I have eigenstates of my density matrix, let me call them VI. VI, if rho acts on VI, it gives me this probability PI times VI. So I goes from 1 to the k. So as I said, I keep only m most probable states, and I can build a matrix. Let me call it this matrix U of this eigenvectors of this most probable state. So this matrix is going to be like it has this rectangular shape. So will be V1, V2, ... Vm. Right. So it has size. So horizontal size is m, and vertical size is 2 to the k. So it's this rectangular matrix U. So if I conjugate my density matrix U dagger rho U, I get just because it's a matrix of eigenvectors of my density matrix rho, I'm going to get a diagonal matrix with this probability, with the highest probabilities P1 to Pm, which I keep, and 0 everywhere, right? So now if I conjugate my density matrix by this matrix U, I get m by m matrix, diagonal matrix for the density matrix. But now I do truncation of my system by conjugating my blocks by this matrix U. So what I do is, all right, let me erase. So rho initially was 2k times 2k matrix, but now I conjugated by m by the U, which is 2k times m matrix, right? So if I do this, I get m by m, smaller matrix.
So how many V matrices are there?
V are eigenvectors, so it's a column of 2k numbers.
You only keep M.
I keep only m eigenvectors of rho, which have the biggest eigenvalues, most probable eigenvalues p. So this p are the biggest, the most probable eigenvalues. They're all basically close to 1 essentially, or they, if I sum them all, they will be almost 1. Yeah, so. All right, so now I do my renormalization by truncating my left and right blocks using this matrix U. So I define a truncated block left k bar by conjugating it by U matrix U. Let me call it U left, k left. So I also have to do this for my operator sigma plus, sigma minus. And so I truncate all my operators which build my Hamiltonian. Right, so that's a truncation So now all of these matrices, when I conjugate them by this matrix U, they become m by m matrices. And m is much smaller. We keep m fixed, or so it's much smaller than 2 to the k. And I can do the same for my environment. So I can build a right-hand side density matrix. It's going to have the same probabilities if it has the same system, right? But vectors is going to be different. Eigenvector is going to be different if it's so. But so I'm going to do the same operation of my right system or environment system. And right. All right, so that's the most important step in this algorithm. And now I can continue building my spin chain, but now using these truncated matrices, truncated blocks. So sure. Yes, so I'm gonna show that. But basically, the statement is that doing this truncation will, of course, introduce some error in my computation. But this error is going to be it's going to be maybe slightly bigger than this truncation error. So. No, but it's essentially if I keep only m states, my size of the Hamiltonian will be fixed. Of my superblock will be fixed with m. It will be 2m squared times 2m squared, and it will be the same for as many sides I can add to my system as I want. That's the yeah. Let me show. It's actually let me finish this. So okay. So now I did this truncation by this matrix U, and I can continue building my block. So now I just continue this procedure. So I can build now k plus 1 left Hamiltonian using this truncated block. So I use this truncated block LK bar and add just tensor with this identity matrix, and then plus this sigma truncated sigma L plus K times sigma minus plus sigma minus LK times sigma plus. So I can continue building my my Hamiltonian, but now using these truncated blocks. And the sigma LK plus 1 will be just now m by m identity matrix times sigma plus, and the same for sigma minus. And I can do the same procedure for my right block. So I can increase my right block by one side using these truncated blocks. So I can write it as identity times truncated block H or K sigma plus times sigma minus bar K plus sigma minus times sigma plus bar, right? So now this left and right Hamiltonians, they are both, they are now 2m times 2m matrices here and here. 2m times 2m. So I added just 1 qubit one to my blocks. And now I can again do the same procedure, so I can combine them and build a super block out of them. So okay, let me. So just repeat what I already did, but now with truncated block. So now I can build a super block which should correspond to chain of 2k plus 2 sides, and it's going to be h l k plus 1, which I defined there, times identity of 2m cross 2m plus identity m cross 2m, h right k plus 1, and a term which connects left and right block, which would be sigma plus L. Right. So now the super block, instead of being 2k plus, instead of 2 to the 2k plus 2 cross 2 to the k plus 2 matrix, it is just 2m square cross 2 to the m square matrix. So it's much smaller. And the sort of the remarkable thing is that if I now find this ground state, ground energy, if you're interested in ground energy eigenstate of this new super block, which was obtained by truncation or by doing this RG, I'm going to get energy level 0 of 2k plus 2 chain. Let me call it maybe bar here. And the statement is that this energy levels or this this wave function, or they the energy level here, it's not going to be exact anymore because I did this truncation, so throw out some degrees of freedom. But if I compare it with energy level exact, so if I just get this numerically and compare it with the exact solution, which here in this model I know, that will be like really very, very small number. So the error of doing this truncation will be very small. In this case, it won't be exactly a truncation error because there are other sources of error in this procedure, but it will be something maybe 1 order less. So if I said if my truncation error was 10 to the minus 10, that doing this would be like 10 to the minus 9, or sometimes it's worse, but for this XY model, it's going to be 10 to the minus 9. Right. And I can just again repeat this procedure. So now I find this eigenstate of this super block. I can again find left and right density metrics, which will be 2m cross 2m. And then I can again do this truncation, keep only highest probable states. Again, just repeat the same procedure again and again, and keep growing my my spin chain to basically to infinity, always truncating it to m by m blocks. And this way I can reach energy levels and eigenfunctions of basically arbitrary size spin chain, quantum spin chain.
So the starting point of the algorithm is, I guess, some small chain that you can run. Is that right?
Yeah, the starting point is that you build the chain without truncation for lowest number, like for small number of qubits, small number of sides. But at some point, when the Hilbert space grows to some big number, you start truncation. And doing this truncation introduces errors in the energy levels or in the wave functions. So you can use this wave function, truncated wave function, to compute expectation values of operators. Because you did truncation, there are going to be errors. It won't be precise, but the errors are small. they do, yeah, they do accumulate, but then still, like if you can, so to lower errors, you can increase number of m, and the error basically quickly decay with m. So if you take m around like 100, it's already almost machine precision type of error. So for us, it's like more than enough. It's a 1 point, and this procedure, when we keep building our chain side by side, it's called infinite DMRG. Let me go with. And also to, so in this procedure, we have this truncation error, which we control, but there's another source of error, which is called environment error, which we don't control. The idea is that when we build Superblock and we project on this truncated state, we also introduce some another source of error which we don't control. To improve another error which we don't control, which is called environmental error, we do what we call finite DMRG. So the finite DMRG, I don't have much time, but let me just quickly say what it does. In finite DMRG procedure, we keep chain size fixed, and then we let's say we build our chain to I don't know, to some something like this, left and right. So this is our system. This is our environment. Let's say we build it to 100 sites, for example. I draw only how many, like 14, but let's say it's 100. Doing this truncation. Now what we can do, we can actually move system and environment back and forth. It's called sweeps. So we can basically now say, let's consider this as a system, this as environment, and do the same procedure, do truncation, and in large environment, make system smaller, and then in large system, make environment smaller. That essentially optimizes better and better our wave functions and improves errors. And that's called finite DMRG, and these procedures are called sweeps. All right, so essentially, okay, so let me, I have a little bit of time, but at the last point, let me try to explain a little bit why we have to, what we do here, why we truncated our density, why we use density metrics to do this truncation. And essentially, the underlying principle here is a variational principle. Essentially, what we are doing, we are looking, using variational principle, we are trying to optimize our true wave function by some truncated wave functions. We're trying to optimize our wave function for our quantum system. All right, let me. It will be. So suppose we have a state psi, which is psi ij I left, j right, where I and j goes to 1 to n, and we can try to optimize this quantum state by state psi fiddle, where I now goes from 1 to m and j goes from 1 to n. and some other coefficients psi I fiddle ij. Let me call now it's alpha. Let me call this index alpha. Alpha j, where alpha now goes to 1 to m, sort of truncated, so alpha much less than I, or less than I, alpha L JR. And we build the states alpha using the states I of our left system, like I 1 to n, matrix U, I alpha, I left. So there are only m states alpha, okay, which is, let's say, much less than m. Yeah. And what we try to do, we try to optimize our initial exact wave function by this psi fiddle. So we try to minimize the norm psi minus psi fiddle. So we try to minimize this norm. And so which is fiddle. Right. And it's going to be 1 minus ij alpha psi j j u j plus right. So we just trying to, we do this optimization of our wave function. So we have to minimize this norm, and we can vary this norm over psi of j. It's be 0. So so it will gives us equation for, let me see. It gives us equation for psi fiddle alpha j equals dagger j. And now if we, okay, so we have, it has to be stationary for the psi fiddles. So if we put it, we get now this equation for psi fiddle. Now we can put it back in this norm, and let me still use it here. So we find that this norm will be 1 minus matrix U I alpha rho I prime alpha, some alpha, where this rho is the density matrix of our state. So from here, we can see that if you want to minimize this norm, you have to do exactly this procedure. So you have to pick this U, this matrix U, to be the eigen, to be the composed of eigenvectors of the matrix rho. So at the end of the day, what we do exactly, we minimize this norm. We optimize this initial state to some smaller state psi fiddle. So this norm at the end is 1 minus sum over highest probability states of this density matrix rho. So it will be I y to m. So that's essentially what underlies this this DMRG principle, is to do optimization or variational optimization of our quantum states. Right? Okay, I think at the rest of the time, I'm gonna just show, yes. Mm-hmm. Yes. I would say any Hamiltonian you choose for 1+1 system, unless if it's highly, the problem could happen if it's highly non-local. If it's just the usual spin chain like Heisenberg model, old spin chain we know, it's gonna work. There's this, of course, subtlety if you're looking for a critical point. Then there's a subtlety when you look for systems at criticality. Because in this case, what happens is that entanglement of 1+1 system grows as a log of the size of the chain. And then essentially, to deal with it, you can increase this this number m, which we truncate with this with the size of the chain. Or you can, there are another methods. One of the methods is called MERA, multi-entanglement renormalization group, renormalization ansatz, where it's designed to work with critical systems. But more like, just a short answer to your question is like, whatever Hamiltonian you choose, 1+1 is probably going to work. Follow, yeah. All right. Okay. So I have, I guess, five minutes, right? Just more. Okay. So let me. So the rest I'm going to just show this Mathematica files, which I uploaded to this GitHub folder, so you can find them and play, and then play with your chain you like, spin chain you like. So next lecture, I'm going to discuss how to use it for Schwinger model, because Schwinger model in 1+1 essentially is a spin chain. All right, so let's just let me just show that it's easy to use. So I think like Mathematica is a language which most of the people know. It's maybe the most inefficient method to do numerical computations, but on the other hand, just to grasp what is done is maybe the easiest. So if you want to optimize really like numerics, you probably need to rewrite it for using some other language. But just to understand the concept is probably the best. All right, so this is just okay. So there's some auxiliary functions which just draw a spin chain. Okay, let's check. So this is the exact solution. It's a single particle energies, this epsilon kn, and then I can build exact ground state or few excited states. So there are these numbers. Say this is for a spin chain of size 8. And this is exact diagonalization. So this file does exact diagonalization. So to do this, you have to define spin plus, spin minus identity. Let me just, so you can print them. So this is this matrices. So then you also need to define big identity matrix 2m times 2m identity matrix, which actually is the tensor product of m small identity matrices. So I wrote a lot of comments. So these are comments, so you can see what is done here. So for example, identity 2 will be 4×4 identity matrix. And okay, so then you can just build the XY Hamiltonian where each term is just this Kronecker product of these matrices. Let's define each term as HI. And then the Hamiltonian itself is the sum of n-1 terms like this. So it's a big matrix. So let's, okay, that will be 2 to the 8 matrix. So, oops. So it's too big to show, but okay. So it's some big matrix. So then you can make it sparse just to speed up diagonalization, and then just ask Mathematica to find its spectrum, lowest line, or highest magnitude spectrum. So first 10 highest magnitude states. So the lowest state is -475, and you can check that it agrees with exact solution. So it does work. So it's very useful just to solve your problem using exact diagonalization, just to be sure that everything works, because DMRG is slightly more complicated, and there could be some errors or some in your code. Now, there was exact diagonalization file. So now let me open the MRG file. Oops. All right, so that's now the MRG, and so there are some, again, functions to draw your spin chain like this. Okay, here again, exact solution. And now let's see step by step how it works. So now we again need to define sigma plus, sigma minus matrices and identity matrix, and also big identity matrix, which now the index is just the size of it. So identity 3 is just a 3 by 3 identity matrix. All right, so the step 1 is we create left and right blocks. Here, just tensor products of sigma plus, sigma minus, and it schematically looks like this. So 2 sides on the left and 2 sides on the right. Then we define the superblock. So we combine this two sides from left to 2 sides from right. So we get the superblock, which is 4 side. And then we diagonalize it. We find its eigenenergy and state, and then we can compare it. So far, it's exact. So there's no truncation here, and the energies agree. Then we can do this, though it's still exact, we still can do this procedure of going to defining density matrices left and right. And so we can define, we can build a left and right density matrix. First, in Mathematica or in numerical language, when you diagonalize superblock, if you build superblock as a big matrix, though if you want to speed up, you should not do this, but if you do this, you'll get one big state, which is now in this case for 4 sides, it has 16 indices. But then you have to reshape your state in this form, in left and right form, psi ij. So it's done by this function array reshape. And now you can build a left and right density matrix exactly as I said, psi dagger or psi dagger psi, and then find its eigenvalues. So for example, let's find its eigenvalues. So as I said, for example, for this 4 by 4 density matrix, the biggest eigenvalue is this, and then it quickly decays, right? So it's 0, 0, 5, and then it's 0, 0, 2. And as I said, the total number of the sum of all eigenvalues must add up to 1 because it's density matrix, as it should be. So now you can build this matrices U, this matrices of the eigenstates of left and right, and then you can conjugate your density matrices from this, and then you can get diagonal matrices as you should. At this point, we don't do any truncation. It's just very small system, so we can do everything exactly, but we still can pass to this new basis of density matrices eigenstates, define new blocks, and then start repeating the procedure again, growing blocks side by side. So we can add one side from the left and one side from the right, and then build the super block like this, and then diagonalize it, find energy state, compare it to the exact solution. So far everything is exact, so they agree. And again, find density matrices, find density matrices, find truncation matrices UL and U, right? And then at this point, yes.
Until now you have not truncated.
Yeah, until now. Now I'm starting truncation, so I keep M. I chose my M to be 6. At this point, I have 3 sides from the left and 3 sides from the right, so it's 2 to the 8. So it's 8 by 8 matrices. So, but I want to truncate it to 6 by 6. This is like just. And now I do truncation, so I keep only M states. So I use mean of M and 2 to the 3. So for M equals 6, it will give me 6 by 6 matrix. So now I truncated my density matrix to 6 by 6 matrix, and you can see the eigenvalues. Like there are 2 big eigenvalues, and then other eigenvalues is very, very small. So the truncation error in this case, essentially is 10 to the minus 6. So I essentially throw out just 2 states, right? My matrix have to be 8 by 8, but I chose it to be 6 by 6. So I truncated only 2 states. And I do this, now I truncate my blocks. So I'm conjugated by this truncation matrix. And then I move forward and I construct 4 by 4. So I add one side to this now truncated blocks. So now I construct Superblock, which is now 8-side system, and then I diagonalize it. And at this point, I already made truncation. So now this eigenvalue I get here, it's not exact. So we can compare it now with exact. And it's different, but the error, so we can see the error here is, well, the absolute error is then like 8 times 10 to the minus 4, but the relative error is 10 to the minus 5, 10 to the minus 5. So it's very small. So that's the procedure. And of course, I did it step by step just to explain, but I would like to write it in a cycle using cycles. So I can just say, now define my cycle, define my truncation side, say m equals 10. And then I can, so I start with this 4-side chain, but then now I can just run a cycle, say to 10 sides. So now it will be in a cycle. So I get like iteration 1, iteration 2, so up to spin chain of 20 sides, and at each point I get my ground energy, and I can compare it with the exact solution and see what is my absolute error in this case, and how it compares with truncation error. So you can see that truncation error is always lower than absolute error or relative error, but it's still kind of the same, maybe 1 order of magnitude more. And these are table of exact eigenenergies. So for example, for spin chain of 20 sides, I get this energy, which is minus 12.38, and exact energy is minus P815. So this the error now is 10 to the minus 3 around, but it's still very precise. All right, so I'll stop here. Thank you.
Yes, thanks for a great lecture. Questions? Yes.
Does the error behave with higher states, so not just ground energy?
If you say it again. Excited states. It's more or less the same. So you can look only for if you look for excited states, you need slightly to modify procedure. So one way is just to, at each stage you need to, when you diagonalize the superblock, you find not only ground state but all lowest excited states. So for example, you want to look at third excited state. So at each stage you need to find 3 first lowest states, construct 3 density matrices, and then take sum of them, weighted sum of them, and repeat the procedure. And of course, yeah, the error would be worse for excited states, but then the whole idea works. So you need to just, maybe you will need to decrease this truncation size to make it more precise.
Also, just in fact, on the board, 10 to the minus 9.
It depends on m, right? So I chose here m equals 10, right? If I want a higher accuracy, I can choose like, I don't know, 16, and then run it again. It will be slightly slower, but you see the error becomes smaller, right? So if you want a higher accuracy, you need to increase m, but still you can go to spin chains of very large size. Even that's the,
when you choose the last time you choose n equals 6 and the total field of space like
8, yeah.
You are almost in the gap here, but
yeah.
Still the relative error.
Yeah, I don't know why. It's just
But somehow, if you say take m equal 100, then even you can make the size of the lattice, you know, hundreds, right?
Yeah, even here, yeah.
And you still get 10 to the minus 5 or
yeah, you still get
less.
very high.
Yeah.
If you want to improve the precision, you need to run what is called finite geometry. So you do sweeps back and forth. I didn't. Okay, I have another mathematical file with it, but that sort of optimizes the wave function even better and then increases precision. So that's.
Okay, well, we still have the Q&A this afternoon, so Grisha can answer more questions. But let's thank him again.